Hello everybody, welcome to our talk, The Recipe for Scalable Frontends. My name is Dan Persa and I'm a delivery lead in the fashion store department at Zalando. My challenge now is to lead the team who is building a next generation CMS. I'm also one of the developers who contributed to Project Mosaic, the one we'll be talking about today.
Hi, my name is Maximilian Fellner, and I've been developing web services and applications at Zalando for several years. I recently also developed a new open source project that aims to make frontends more scalable, and you'll be hearing about that today as well.
Zalando is Europe's leading online fashion platform. You might be familiar with our company as it's pretty well known in Germany. Here's how our fashion store looks like. Here are some numbers to show why our recipe for scaling works. It's because we are dealing with scaling every day. Our company is present in 15 countries. We have more than 21 million active customers, and last year we had a 3.6 billion euro in revenue. We have a great team of 1,600 talented people in tech. Now that you have an idea about the scale at which our company operates, let's go to our recipe for scalable frontends. Every recipe has two important things: the ingredients and the instructions. We'll soon discover ingredients related to scalability and ingredients related to scaling, and ingredients related to frontends. We'll get our hands dirty and we'll get into the technical instructions as well. Let's take a look at our first two essential ingredients we will use in our recipe: scaling the team and scaling the architecture. Without these two ingredients, scaling the frontend might not even make sense, as the system operates at such a low capacity that scaling is not a problem worth tackling. Let's dive deeper and see why each of these ingredients is important. First, we want to be able to scale our tech team. What does this mean? We want to attract new, talented people to grow the team. The reason you want to scale your team in general, and specifically in our case, your front-end team, is because there are plenty of new features to be added to existing products or new products to be built. Of course, this can be achieved if there are more front-enders leaving the company than compared to the ones which are coming. So another requirement would be to keep the existing team happy. Putting somebody spend 4 hours every week to deploy a monolith doesn't make anybody happy. Also, having the front-end developers waiting for a monolith to compile, let's say, Java classes is also not appealing. Next point, we want diverse people who are able to see the same problem from different perspectives. The more ideas you have, the more likely it is to find the best one. Diversity leads to innovation. We also want to actively encourage innovation. Innovation is keeping the company on top of the competition, and it can be encouraged by, for example, organizing hack weeks or giving the teams time to build prototypes and experiment. A happy team is an innovative team. For a happy, innovative team, it's easy to talk about the project they are working on, like me and Max today, and attract more talented people. As you can see, all of these 4 points are interconnected. Let's look and see how, by applying these principles, our company was able to scale its tech team. Here's how our tech department evolved over time. As you can see, we started in 2008 with PHP and MySQL, Magento actually, and one of my colleagues drew this chart 2 years ago to demonstrate the growth of our apps in comparison to the growth of our tech team. What you can see here is more or less linear growth for both the number of apps and the number of employees. Starting with 2015, this graph had to be slightly adjusted. As you can see, the number of apps exploded. We have more than 500 now, and since then, we started to have plenty of open source projects in GitHub. The number of people in tech is more than double compared to 2 years ago. So looking at these numbers, you might ask yourself, how can this be possible? The answer is simple. 2 years ago, we introduced a new concept, radical agility. We at Zalando understand radical agility as a way of running your business based on purpose, autonomy, and mastery. To describe this in one sentence would be trust instead of control. The final goals of radical agility are being represented on the edges of the slide: increase innovation and increase productivity. What's important for today's talk is that radical agility changed the communication structure within our tech department. We started to be organized into small, autonomous teams, which are trusted and accept responsibility. So here we have our first ingredient: scaling the team. Hire a diverse team, give them the freedom to self-organize, give them a clear purpose, and trust that they'll deliver great features. Reorganizing the team has consequences on the architecture as well. Let me introduce Conway's law. You might be already familiar with it. Organizations produce designs which are copies of their communication structures. As soon as the company reorganizes a team, the architecture also has to be changed, which brings us to the next ingredient: architecture scalability. What do we want to achieve here? We want many teams working in parallel at different features without interfering with each other, team autonomy. We want them to deploy independently. We want to give them the possibility of continuous deployment in case they want to do that. We want programming language diversity. We want to use the right tool for the job. In our case, we used to be a Java-based company. Now we are putting more and more languages to production. A/B testing. Adding and removing features really fast drives the product forward. Experimenting with features is a great way to drive the innovation on the product side. But wait a second. These are some of the promises microservices make on the backend side. So the backend side is easy somehow. We fulfill these promises by creating APIs owned by teams. The question is, do microservices solve the front-end problems we have? Do these promises apply here as well? Let's take a look on a traditional way of solving the front-end problem. The traditional solution without microservices would be to have a front-end monolith. As backend teams own APIs now, we can call those APIs from the more lightweight web application. The web app gets contributions from multiple front-end teams. Let's look again at what we are trying to achieve. Are front-end teams working autonomously? No, they are not. They still depend on each other as they are contributing to the same more lightweight monolith. Can they mix different tech stacks? Not really, as somebody has to choose a framework for the common front-end. Can they deploy independently whenever they want? Not really. They are still bound to a release cycle. So it seems that avoiding front-end microservices and solving the problems we have is not an option. We somehow have to make it work. Meet Project Mosaic, microservices for the front-end. Mosaic is a set of services and libraries, most of them open sourced, together with a specification that defines how its components interact with each other. The goal is to support a microservices-style architecture for large-scale websites. While decomposing the backend into microservices is a widely adopted approach to achieve flexibility in both development and operation, most front-end solutions are still running as monolithic applications. Mosaic addresses this issue by using fragments. Fragments are services that render HTML that is composed together at runtime according to template definitions. The fragments are front-end microservices owned by different teams. Teams should be able to develop, deploy, and operate these microservices independently of each other. What's happening inside of a fragment? We can render HTML, fetch data, and we can respond to AJAX requests. Ideally, there is no business logic within these fragments. None of these actions are mandatory. The ones implementing the fragment can choose. As a result, fragments can be iterated over very rapidly, be more flexible in technology choices, and can benefit from the extreme development pace of today's front-end technologies. As I said, in this new setup, teams own their own fragments. They are able to choose the technology for them and they can deploy them independently. Each fragment is able to do calls to different APIs, and each fragment renders a part of a final page. how does the final page get assembled from the HTML rendered by each of these fragments. On top of the fragments, we have another service called the layout service. The layout service puts together the content rendered by fragments. It uses templates to know how to assemble them. We'll talk about templates soon. The assembled content is streamed to the client through a router. The router is necessary to handle API calls, mobile app calls, or help in the migration from a legacy system, for example. Let's get from these microservices from the front-end idea to our Mosaic implementation. We have names and implementations for both the router and the layout service. Skipper is our router, and Tailor our layout service. Skipper is a piece of software we built in-house, open source right now, and it is the entry point for every request from the browser, excluding the static resources. It acts like a reverse proxy and will delegate the request based on some internal routes to one of our new microservices or to a legacy system like Jimmy there, in case a migration is happening. It has other functions like security features, and for more details, please check out our GitHub repository at Zalando at github.com/Zalando/Skipper. Tailor is our layout service. It's another project which we developed as open source. It uses streams to compose web pages from fragment services. It loads the content of all fragments from the template in parallel, offers nice error handling and fallback features. Here is how our template looks like. As you can see, most of it is HTML with some special tag, fragment. This tag acts as a placeholder where Tailor will insert the content it gets from each specified fragment. One of the fragments has to be marked as a primary fragment. This is the fragment which will give the final HTTP status of the page. You might have noticed that this concept is similar to Facebook's BigPipe. The difference is that with BigPipe, things get assembled on the client side. For SEO and user experience reasons, we want most of our content to be streamed in order. We can achieve a similar behavior as with a BigPipe by using that async attribute within the fragment tag. Let's look at an example. We have a request for the cart page from Skipper, the router. Skipper knows that the /cart URL should be handled by Tailor and forwards the request to it. Tailor needs the template for the /cart URL, and if it doesn't have it cached, it asks Quilt, a RESTful API, for it. Tailor gets the template, looks at it, and sees that it has to call the header fragment, the cart fragment, and the tracking fragment. It does all of those calls in parallel, puts everything together according to the template, and returns the response to Skipper. The status code gets set by the cart page, as the cart is the primary fragment. A fragment may provide some JavaScript and CSS as well. Besides the static HTML, Tailor will look for additional script and style sheet assets inside of the link HTTP header of the fragment response, and will inject the corresponding links into the head section of the final page. The JavaScript must be defined as an AMD module that exports a single function. When finally executed on the client, this function will receive the DOM element of the fragment as an argument. Here is how our Zalando cart page looks like after it gets assembled by Tailor. The final page is assembled from these three fragments: the header fragment, the cart fragment, and another fragment which is not visible, the tracking fragment. Each of these fragments are managed by different teams. So here is our second ingredient, scaling the architecture. Come up with an architecture which allows team autonomy, independent deployment, encourages a mix of tech stacks and experimentation. Right now, Mosaic is live, and we have quite some traffic on it. Last year on Black Friday, we had more than 20,000 requests per second on Skipper, and we are expecting even more this year, as Black Friday will soon come again. So far, we have showed you how a single large website can be split into smaller fragments. Max, what's next?
Well, as it turns out, web applications and websites are a lot more complex today than they used to be. They contain lots of dynamic elements, interactive elements, powered by JavaScript, and they serve large amounts of dynamic content. Let me show you how we think we'll manage all that. So our website, or as we call it, the fashion store, is actually a highly dynamic application. Here's an example of how the fashion store might be divided into multiple fragments. Each fragment can have some sophisticated interactive behavior and maybe talking to multiple backend APIs. Naturally, we update the content very frequently on the fashion store with the latest styles, trends, and product information. The content itself is also dynamic and might change for different users because of personalization. So with this in mind, what is actually the best way to implement the fragment? There are three important things that we want from our fragment. First, it must provide a modern and interactive user experience, similar to a modern web application. Second, it needs to support the dynamic and frequently updated content that we want to deliver to our customers. And lastly, we want to make sure that the fragment preserves the consistent look and feel that our customers have come to expect everywhere within the fashion store. So a very simple fragment might only render some static content. Obviously, this has many drawbacks. First of all, this implementation is way too manual, and updating the content means changing the whole fragment and likely redeploying the web service. Also, the user experience is likely to be quite inconsistent between different independent teams. So here's another idea. Instead of rendering just static HTML, a fragment may react to requests dynamically, fetch some external content, and send back a computed response using an HTML template engine. While this is already a lot better than the first approach, many fragments are still going to deliver inconsistent user experience as implementations differ. The biggest drawback, however, is that in this implementation, JavaScript is not part of the fragment. So we've come up with a better concept. We think fragments should use existing, reusable, and shared JavaScript components. Although those components run dynamically as code inside the browser, they can also be readily transformed into static HTML on the server. This kind of code that allows server-side rendering is also sometimes called isomorphic or universal JavaScript, and there are many popular solutions that you've already heard about today that support this. For example, React or Vue.js. Now, let's take a closer look at how this idea is supposed to work in detail and how it fits together with the Mosaic architecture. So because the fragment is supposed to use only existing JavaScript components, we start out by describing the content that we want to serve on the website with abstract JSON. If we take React components, for example, we can show that they are easily described with basic JSON. Every component has three attributes: the type, which can be the name of a DOM element, like div or h1, a set of properties or props, for example, the attributes of an HTML element, and a list of children with more components, or simply plain strings. So the next step for the fragment is to take those JSON descriptions and transform them into the JavaScript and HTML that will be sent to the Tailor Layout service. During this process, the code from common component libraries, for example, modules on NPM, can be included. So how does this code generation work? As we've seen before, React components are actually quite simple. If we know the type, the properties, and the children, we can easily produce a hierarchy of nested function calls of the createElement function. Once the code is generated, we simply evaluate it to create a React element and then use the render-to-string function to turn it into static HTML. The big advantage of this solution is, of course, that the generated JavaScript is universal, so it can run not only on the server, but also on the client. So this looks like a really promising approach. In fact, we've already implemented it and released it as an open source project. We've called it Tessellate. The project comprises two major parts that I'll talk about in more detail next: the bundler and the renderer. So in Tessellate, the process of transforming JSON into JavaScript code is performed by the bundler in 4 steps. First, the JSON is passed as an abstract syntax tree. Next, we use that to generate JavaScript code. In the third step, Tessellate uses Webpack directly in memory to compile a universal bundle from that code. Finally, those bundles are exported to a remote content delivery server for later use. So let's expect an example of the code that Tessellate generates. It's actually just a single React component. The component types used in the JSON description are turned into import statements. There can be default imports and named imports. The rest of the JSON description is turned into createElement functions with props and children. However, there's more that we can do here. Right now, all the properties are statically encoded directly inside the JSON description. But of course, the root component can receive props from an outside source. So Tessellate has a way to inject the external properties into the compiled React components during rendering. The values of those properties are not known ahead of time, but they can be referenced relative to the root props using JSON pointers. In addition to that, we can also bundle some properties during compilation as default values and merge them with the external properties. A common problem with React components rendered on the server is the so-called rehydration. We need to ensure that the same properties are used for server-side and client-side rendering. Tessellate solves this by adding an attribute to the root component that stores all the props as an inline string. This attribute will be present inside the static HTML, allowing us to receive the props inside the browser. So finally, the generated JavaScript exports a function that the Tailor API demands. This function is going to be called on the client side inside the browser, and it receives the DOM element of the fragment as an argument. This element also happens to be the parent of the root component. So inside the function, the inline props are extracted, and the React component tree is mounted on the parent element by calling the render function. So to summarize, the Tessellate bundler is a microservice that transforms JSON into JavaScript. The JavaScript is compiled into portable, universal UMD bundles using Webpack in memory. The main bundle exports a root component and a render function for Tailor. The root component provides an interface to inject property values. The properties can be referenced using JSON pointers, and they're inlined as a string into the HTML for rehydration. We'll come back to this in a moment. We've also seen how components can use external libraries referenced in JSON by the respective node module names and the names of the exports of those modules. So this was the first part of Tessellate, the bundler. The other part of Tessellate is the renderer. This is actually the fragment that renders the HTML. When this fragment receives a request, it fetches the precompiled bundles from the CDN where the bundler placed them before. Next, additional data can be loaded from external sources. Then Tessellate evaluates the code and finally renders static HTML. So here's what the implementation of that process looks like. First, the precompiled bundle is downloaded. At this point, Tessellate can use the available information in the current HTTP request to decide which bundle exactly to choose. Next, the code is evaluated inside the Node.js virtual machine, and the exported root component is extracted. As we've seen before, this root component has an interface for external props, and we can load some data to provide those. In the final step, the root component is instantiated as a React element and injected with the external props. Now the element can be rendered into HTML and sent back to the Tailor layout service. If it looks like the renderer is a lot simpler than the bundler, then that's because it is. The Tessellate fragment has only 3 jobs: download the precompiled bundle, fetch some additional external content, and render everything as HTML and send it to Tailor. This is how the complete picture looks like. We have the Tessellate bundler microservice that takes an abstract description of React components written in plain JSON. It compiles the description into universal JavaScript, then can run on both the server and inside the browser. And then there's the Tessellate fragment, which renders the compiled bundles and any additional external data into static HTML according to the API demanded by the Tailor layout service. This architecture meets all our requirements for the fashion store. With JavaScript components, we can achieve a modern and interactive user experience. Content can be externalized and updated separately. And because we're using shared component libraries, the look and feel is going to be consistent everywhere. In fact, this was the last ingredient of our recipe, scaling the content. We use small, reusable, and shared JavaScript components to push large amounts of content. The components are consistent between many independent teams, and they decouple layout and data for greater scalability.
So here is our recipe for scalable frontends. We have scaling the team, scaling the architecture, and scaling the content as ingredients, and radical agility, Mosaic, and Tessellate as the instructions. You can find more details on our project website, www.mosaic9.org. Thanks a lot for watching our presentation. Are there any questions? So they are microservice specific. What's happening is that each fragment can specify within their HTTP link headers links to different style sheets and JavaScript files. And what Tailor will do, will inject those links, which are probably some CDN links, into the head part of the final HTML page. So they will get loaded. So each of them are specific. We also have a common library in our implementation, which we load for all of the microservices. A common JavaScript library and CSS library.
Where does the actual logic come into the components in the front end? What you've showed so far was just like creating divs and links, but if I like, where does the logic come in if I click on a certain checkbox or whatever?
Yes. So the examples were intentionally simple, but we would expect that any kind of React component that you can build can also be rendered with this Tessellate fragment. So the idea would be that, for example, you have some interactive element that fetches a list of articles from a backend API and then displays them inside the browser. And then maybe you can click on an article and it opens a pop-up and you can place the article inside the shopping cart. All of this functionality would be contained inside one React component, or maybe a tree of React components. And then you would just add this inside your JSON description. It would be executed on the server during server-side rendering, so all the data would already be fetched, the HTML would be ready, and even if JavaScript is not enabled on the client side, you would have this article data. And then finally, because the JavaScript is also forwarded to the browser, the interactive functionality is there.
Thanks a lot for a great talk. My question is that how do you manage the state that is in the route, as well as how do you manage the connection between these fragments? How do they talk to each other and have that binding?
So let me start with the fragments. They talk to each other using an event bus, an internal event bus. And the other part of the question, what was the first part of the question? So the way the routing works is that we have a customer cookie for each of our customers. So we are able to, we know what, in which state each of our customers is. So Skipper is able to decrypt the customer cookie and see, well, how the page has to be rendered. Does this answer your question?
Well, I guess maybe a different way to look at it is if you were to have actually a full-scale React-based application that manages some kind of state, then that might be lost when you navigate away to a different page that is managed by different fragments. So as long as you stay within the same context, if you don't navigate around on the page, you can do inside the fragment JavaScript whatever you want. So you can manage your own state, you can persist it to local storage and retrieve it later. If you navigate to a different context, then you would lose that state. So in that case, we would expect that all this state is actually managed on some backend on the server side. So for example, if you place something into the shopping cart, this is not state that is managed on the client side. It's already something that happens on the server. And then this is updated again when you reload the page or navigate to a different part of the page.
So in this regard, you're not able to keep the fragments really separated from each other, right? Because basically they should have some binding together if there is a event bus, and there should be some team or some, I don't know, service or anything that is taking care of this binding between these different fragments. Then if that is in place, then you won't be able to have different deployments for different fragments, because
so the fragments are not linked together. What's happening is that each fragment emits events, and all of the other fragments are, I'm talking about the client side. So on the client side, each fragment, some of the fragments emit events, and all of the other fragments are getting those events, and they can filter them. So it's and react to them. So they are completely independent. Of course, sometimes in special cases, you need to know how to treat that event. So that's some kind of a binding, but that's not a usual case. So that doesn't happen a lot.
Okay. You said that you have common library that of the components that you use to keep the consistent state, and how do you? And then you want to have autonomous teams that can create things on their own. So do you have a team that takes care of these components? And if the team needs something, they need to ask the core team to create these components. So they are kind of dependent, right?
Yes, so we have this common library, and this is a compromise we had to make for team autonomy. This is because consistent user experience is really important for us. We want many teams deploying these fragments, but we want our customer to see our fashion store as it was designed by one big team. So as this consistent user experience is so important, we decided to have this common library. We have a team which is managing this library, and what they are doing is that they are releasing newer versions, and they give time to each of the teams to react on those new versions and see if their fragment still works with a new set of components. Usually what we try to do is always have them backwards compatible, but that's not always the case. But we usually launch this library on release and have the teams use it for a while, and then we go live with it. Only after we make sure that everything goes well on our staging environment.
Thank you.
Don't you think that there is a risk of like code bloat if, for instance, one team chooses to use Vue or Riot, Angular, and the client is loading React and Vue, and I don't know, for the different fragments?
Well, yeah, I can answer that. So as I mentioned in in the first part of the talk, we have teams which are trusted and accept responsibility. So we trust our teams that they will do the right thing. We don't enforce it. Also, for our fashion store, we have this constraint of using the React library, so we don't really allow other frameworks to be loaded. This is not a hard constraint. We just trust our teams that they will do that. So it's part of our guidelines, let's say.
Thank you.
Also, on a technical note, just to quickly expand on that, because there was a similar talk today where the answer to this question was that all teams should just include the dependencies into the bundles, and then you have multiple versions of, for example, React on the page. We do actually have a mechanism inside the front end that is based on AMD modules that you can externalize your dependencies, say React, and then those common dependencies will be present on the website, so you don't have to include them inside the bundle.
I would like to learn more about the event mechanism, like if a component sends an event but nothing actually receives it, does it stay? Is it durable? Like when I close the page, everything is gone, no JavaScript is working anymore. Are all of those stored in the local storage or session storage, or are they all gone as well?
Okay.
Well, so the event mechanism is right now not very heavily used on Zalando. So we're not making it very reliable, if I might phrase it like that. So we don't persist anything, there's no queue. If there's no receiver for the event, it just dissipates. We use it right now only for some smaller use cases, as in practice we found that it's not so important most of the time that fragments communicate with each other, because they're mostly communicating with backend APIs.
Okay, so I see no questions. Thanks a lot, and well, happy party.